Hey guys, my name is IBM and I want us to continue with our paper 4 nuclear physics paper 4 series. So remember we are dealing with the nuclear physics and this is A-level physics 9702. This is paper 4 and I want us to go to lesson, this is going to be lesson 3. So I want us to talk about stability today, having looked at the mass defect and having looked at the meaning of binding energy. Remember in our previous lesson we said, in lesson 2 we said the mass defect was actually the energy equivalent, the binding energy was the energy equivalent of the mass defect. And from our understanding of binding energy as the energy required to separate the nucleons of a nucleus to infinity, or the energy required to bring nucleons from infinity so as to form a stable nucleus, we noticed that the most stable nuclei are those which are going to have the highest binding energy per nucleon, because it means that if a nucleus is very stable, then it requires a lot of energy to separate its nucleons. So it's like the most stable nuclei are the ones which are going to have the highest binding energy per nucleon. So if I was to sketch a graph of binding energy per nucleon, the graph would look somehow like this. I'll just highlight the most important nuclei from this graph. The first one I will highlight is hydrogen, deuterium actually, not hydrogen, deuterium H21. I'll also highlight iron, Fe 2656 or 5626, and I'll also highlight uranium 23892. These are going to be the determining nuclei on this graph. So we notice that at the bottom of the graph, a graph of binding energy per nucleon against a nucleon number at the bottom of deuterium, at the bottom of the graph, we are having deuterium H21. Note that we are not seeing H11. There's a reason as to why H11 is not on this graph. And we notice that iron 5626 is at the peak, at the highest point on this graph, which means most likely iron 5626 has the highest binding energy per nucleon, which is in most cases one of the most stable nuclei. Then on the other side we have uranium 23892, and you notice that uranium 235 has a bigger nucleon number and its binding energy is less than that of iron 5626. So what is important for us to note is that it seems like around this region here, nuclei with a nucleon number between 50, 60, in this region here, 50 to 60, it's like nucleon with nucleon number between 50 to 60 have the highest binding energy per nucleon, and therefore this region here could be called the region of stability. Then as you go beyond 60, the binding energy per nucleon slightly starts decreasing, which means nucleons nuclei with a nucleon number greater than 60 are less stable, and nuclei on the left-hand side, that is with a nucleon number less than 50, are also having a smaller binding energy per nucleon, therefore they are less stable. So this is exactly what I'm saying. So this region here is going to be called the region of stability, the most stable region. And then what I've mentioned also is that the nucleus is more stable if it has a higher binding energy per nucleon. It would be more difficult to break up the nucleus as more energy is required to separate the nucleons. So if iron 5626 is the most stable nucleus, it means it's very hard to split its nucleons further apart or to infinity, because the the force which holds the nucleons together is extremely strong, that it would require a lot of energy. The more energy required to separate the nucleons, the greater the binding energy per nucleon. So the most stable nuclide can be found at the peak of the curve. It corresponds to the element iron 5626. So this is most likely going to be the most stable nucleus. And we are saying it has the greatest mass defect. And because it has the greatest mass defect, it will have the highest binding energy. It will also have the highest binding energy per nucleon. Therefore, it is going to be the most stable. So binding energy is a measure of stability, and the higher the binding energy per nucleon, the more stable the nucleus is. And the graph of binding energy per nucleon, such a nucleus will be at the peak. But of course, for examination purposes, like the question of sketching a graph of binding energy per nucleon has appeared almost 3 times. So for simplicity, the graph may be sketched like this. Many times, my students sketch the graph like this, where you just sketch a continuous curve with a peak at around 56, around here. This is where we expect iron to be. This is around 56. Around 56, that is the highest binding energy per nucleon, which corresponds to iron. Then the other side, we expect uranium 235, the other side, and somewhere here we expect deuterium. So this is a graph of binding energy. This time it is not in joules, it is mega electron volts. That's why I said for iron, the binding energy per nucleon is between 8 and 9 for iron, for the greatest, or for the nuclei with the highest binding energy per nucleon. It's between 8 and 9 mega electron volts. So you should be able to sketch such a graph with a peak, its peak at around a nucleon number of 56 in an exam. So typically, very stable nuclides have binding energies per nucleon of about 8 mega electron volts at about nucleon number close to 50. So 56 is iron, and its nucleon number is about 8 point something. So this is where the potential well for every nucleon is deepest. What do we mean by potential well for every nucleon being deepest? It means to just pull out one nucleon from the nucleus would require a lot of, or the greatest amount of energy. That's what we mean by potential well. The greatest amount of energy being deepest. It means a lot of energy, or the highest amount of energy, is required if the nucleus has a nucleon number close to 50, or around in that region between 50 and 60. That's where the binding energy per nucleon is greatest. I also want you to note that the graph here is supposed to start from deuterium, which is H21. Remember, it starts from H21. And the question was, why isn't hydrogen or H11 on that graph? Why isn't H11 appearing on that graph? If you recall the definition of binding energy as the energy required to separate the nucleons of a nucleus to infinity. When I look at H11, it is just one nucleon. It is just one nucleon. We cannot again separate one nucleon. So the word binding energy does not apply to a single nucleon. So hydrogen H11 is a single nucleon, thus does not have binding energy. so cannot be included on the graph. If you want to include it on the graph, then you will put it against nucleon number 1, then binding energy per nucleon is 0. So if you want to add it, you will put a 1 here and then 0 on the y-axis. So it will be at that point there. So, however, hydrogen H11 being a single nucleon, many times it will not appear on the graph of binding energy per nucleon because it is a single nucleon, therefore it does not have any binding energy. Okay, so having established the fact that nucleons which are very close to whose nucleon number is close to 50 or around 56 where we expect iron to be, are extremely very stable and have the greatest binding energy per nucleon, then what happens to lighter nuclei and what happens to heavier nuclei? Of course, when we look at the graph, lighter nuclei must gain stability. And how will lighter nuclei gain stability? Their nucleon number should be increased so that it tends towards the region of stability, which was 50, around 50. This was the region of stability. In other words, the nucleon number should increase to around 50 something so that the nucleus has a higher binding energy per nucleon. And if it has a higher binding energy per nucleon, then it is most likely going to be very, very, very stable. So it implies that lighter nuclei, because they have a smaller nucleon number, the only way their binding energy can increase is by combining to result into products which have a higher nucleon number. And if the nucleon number tends towards the region of stability, then there will be the binding energy per nucleon is going to be higher. So it's like lighter nuclei must combine, which process we shall later on call fusion. Then on the other end, heavier nuclei, those ones with a greater or a bigger nucleon number, the only way their binding energy can increase or can become higher is if they split into relatively lighter nuclei so that the nucleon number tends towards the region of stability. So that process we shall later on call it fission. So there are two processes we are going to discuss here, fusion and fission. The lighter nuclei must combine to increase their nucleon number so that their binding energy per nucleon increases or tends towards the region of stability. Then the heavier nuclei must split to reduce their nucleon number so that the nucleon number, the resulting nucleon number also tends towards region of stability. So we have two terms here. On the left-hand side, we have fusion coming together, and on the right-hand side, we have fission splitting. So let's first understand what we mean by fusion. Let's start with what we are going to call nuclear fusion. So like I have mentioned, nuclei with low mass numbers or low nucleon numbers may undergo what we call nuclear fusion under certain conditions. In general, nuclear fusion is possible as long as the final product has more binding energy per nucleon than the reactant. So if you have, for example, helium, it must combine with another nucleus to result into a bigger nucleus so that the binding energy per nucleon is higher. So fusion is possible if the final product has a higher binding energy per nucleon. If the final product has a lower binding energy per nucleon, then we cannot say that fusion is possible. The enormous or the large amount of energy generated in the sun is due to this process which we call nuclear fusion. In fact, what happens in the sun is that deuterium nuclei combine. Deuterium, that is the isotope of hydrogen, that is H21. So what happens inside the sun is that deuterium nuclei combine to form helium. In the process, a vast amount of energy is released. So energy released in the fusion process is very much greater than the energy released in the fission process, as we are going to discuss later on. However, deuterium, I was talking about an example of nuclear fusion, which was the generation of energy from the core of the sun. At the center or at the core of the sun, there are millions of deuterium nuclei or deuterium atoms, as you may want to call them. These ones combine. In the process of combining to form maybe helium nucleus, or to form a helium nucleus, a vast amount of energy is emitted. That energy is called binding energy still. But remember, the deuterium nucleus, which is H21, must combine with another said deuterium nucleus to give us helium nucleus He32. Of course, this will be accompanied by a neutron if we try to balance this equation. But I'm only interested in the nuclear number. The deuterium nuclei had a nuclear number of 2, but the resulting product has a higher nuclear number. That means the binding energy is most likely going to be greater, because as the nuclear number increases, it is tending towards the region of stability. So helium-3 has a greater binding energy per nucleon than the deuterium nuclei. Therefore, the nuclear fusion reaction is possible. So this is exactly the reaction which takes place at the core of the sun. The deuterium nuclei combine to form helium, a helium nucleus plus a neutron. This is accompanied by a vast amount of energy. Unfortunately, there is a problem with deuterium nuclei. And what is that problem? This explains this statement which I say that energy released in the fusion process is very much greater than energy released in the fission process. I will explain that in more details later on. However, also note that the deuterium nucleus or the deuterium nuclei are both positively charged. So this now brings a problem. The deuterium nuclei are both positively charged. And if they are both positively charged, then there is a problem. And what is that problem? Bringing the deuterium nuclei together to fuse in order to generate a helium nucleus would require vast amounts of energy, or they would require the deuterium nuclei to be having a high kinetic energy. The reason is because deuterium is positive, each of them is positive, and they are most likely going to repel. So they should have a high kinetic energy to overcome the repulsive force between them so that they can combine or they can fuse from helium. This means it is most likely that the nuclear fusion may not be modeled on the Earth's surface, because bringing the deuterium nuclei together may require a lot of energy to overcome the force of repulsion. That's why this only occurs at the core of the sun, where the temperature is millions of degrees Celsius hot and the pressure is extremely high. Such conditions at the core of the sun are hard to model on the Earth's surface. So, lighter nuclei are now combining to form a heavier nucleus. That's what we are calling nuclear fusion. Lighter nuclei are combining to form a heavier nucleus. That's what we are calling nuclear fusion. And what is very special here is that the final product has a higher binding energy per nucleon. The final product has a higher binding energy per nucleon. In other words, the final product will also have a higher nucleon number. Therefore, because energy must be released, it means the total mass of what is formed is going to be less than total mass of the reactants. Not the nucleon number, but total mass. Remember, the mass difference is compensated for by emission of energy. The mass defect or the mass difference is compensated for by the emission of energy. So the total mass of the products this side is less than the mass of the reactants the other side. The difference in the mass is compensated for by emission of energy, and that energy can also be considered to be the binding energy. So that is nuclear fusion. On the other hand, we have what we call nuclear fission. So within the nucleus of an atom, the nucleons experience both attractive and repulsive forces. Of course, the attractive forces are due to the strong nuclear force, or we call that the nuclear glue, which tightly binds the nucleons together, the strong nuclear force. Then when we talk about the repulsive forces, if two positively charged nuclei come close to each other, they are most likely going to repel. That is the electrostatic force, which is given by Coulomb's law. that you'll explore in a unit called electric fields. So there are two forces most likely. The attractive force, which is provided by the strong nuclear force, which or the nuclear glue, and then we also expect the repulsive force, which is due to two positively charged nucleons, most likely going to repel because they have the same charge, since like charges repel. However, I want you to note that stable nuclei have approximately the same number of neutrons and protons in the nucleus. If they have approximately the same number of neutrons and the protons in the nucleus, it means if I divide the number of neutrons with the number of protons, the ratio is approximately close to 1. In heavier nuclei, for example, uranium-235, there are many neutrons compared to the number of protons. For example, uranium-235 has 235 nucleons, which means there are 143 neutrons, and it also has 92 protons. So if I try to find the ratio of neutrons to protons, that will be 143 divided by 92. And 143 divided by 92 is approximately 1.55, which is very close to 2. So it means this is unstable. If we look at iron, for example, iron 56, let me look at iron 56. If we look at iron 56, 26, and we try to look at the neutron to proton ratio of iron 56, 26. Iron has neutrons, 56 minus 26, that is 30, divided by the number of protons, which is 26. And if you press your calculator, 30 divided by 26, this is 1.2, which is approximately 1. So, and iron is the most stable nuclei, one of the most stable nuclei. Therefore, it means for neutrons, or I mean for nuclei whose number of protons is very close to the number of neutrons, such nuclei are extremely stable. Such nuclei are extremely stable. For nuclei whose neutron to proton number is either much less than 1 or much greater than 1, such nuclei are going to be very unstable. That's why we are saying on the left-hand side of the region of stability and on the right-hand side of the region of stability, all the nuclei are not stable. Helium, for example, or let me start with deuterium H21. Now, many people would want to think that deuterium H21 is going to be very stable, but still its binding energy per nucleon is extremely low. Therefore, it is very unstable. But in general, we are saying that nuclei whose neutron to proton ratio is very close to 1 or is approximately 1, they are most likely going to be stable. And in nuclei whose proton to neutron to proton ratio is much less or much bigger than 1, they are going to be very unstable. So let's think of heavier nuclei then, such as uranium-235, 238. If we have already an excess number of neutrons, it means any further increase in the number of neutrons in such nuclei is likely to cause the nucleus to undergo what we call nuclear fission. It's already unstable because it has an extra number of neutrons. So it means if we increase the number of neutrons further, such a nucleus will not last. It will be extremely unstable, and this will lead to its disintegration. And that's what we are going to call, or that's what I'm calling, nuclear fission. So for nuclear fission, therefore, we are looking at a heavy nucleus, such as uranium-235 or uranium-238, splitting because it already had an excess number of neutrons, and again we added an extra number of neutrons, which made it to be extremely unstable. For example, uranium nucleus, it is absorbing a slow-moving neutron to result into another uranium nucleus, which is extremely very unstable, and in no minute or in no seconds to now disintegrate into two daughter nuclei. This is of course accompanied by neutrons, and such daughter nuclei will have a smaller nucleon number. If they have a smaller nucleon number, it also implies that they will now be the nucleon number will be tending towards the region of stability. So in general, heavier nuclides tend to disintegrate into lighter, more stable nuclei. Heavier nuclides tend to disintegrate into lighter, more stable nuclei. This should be plural. Nuclei. Fission fragments have a greater bind, or the products, which I'm calling the fission fragments. Those are the products. The products will have a greater binding energy per nucleon, just like the products of nuclear fusion. Of course, they will have a less mass per nucleon than the original nuclide, because that smaller mass is going to be compensated for by emission of energy. So in both nuclear fusion and nuclear fission, energy is being released because the difference in total mass on both sides is compensated for by the emission of energy. A simple example is we have considered uranium-235, which may absorb a slow-moving neutron, and that means, remember, it already had 143 neutrons. That means when I add another neutron, it means I now have an extremely excess number of neutrons. Therefore, it will not last for long. It will simply disintegrate to gain stability. So the equation would be uranium-235 absorbing a neutron to give us uranium-236. Uranium-236 may not last a second. This will give us I don't know which. This is xenon, I think. Xenon 144, 54, and strontium 9038. For us, we don't need to remember these. That is for chemistry, but whatever is required will always be quoted for us in the equation. So to balance the equation, 2 neutrons are given in this case. According to this equation, I hope I balanced it correctly. 144 plus 90. 144 plus 92, that is 236. 54 plus 38, I think that is 92. Okay, so that is the equation. So we start with uranium, which absorbs a slow-moving neutron to form uranium-236, which is extremely unstable, which immediately disintegrates to give us xenon and strontium. Look at the nucleon numbers. The nucleon numbers are now smaller than the original nucleon number, so we are tending towards the region of stability. Therefore, the binding energy per nucleon for the new nuclei formed is going to be relatively higher. So that's what we are calling nuclear fission. So another common example is, this is going to be the most common example, where uranium-235 absorbs a slow-moving neutron to give us uranium-236, and uranium-236 does not last does not last for a second. This immediately disintegrates to give us our barium-14156 plus krypton 9236. When I try to balance the equation, I think this is 3 neutrons, 141 plus 95. I think that is 236. 56 plus 36, I think that is 92. Okay. So the processes we have been talking about here, where a nucleus, which already has an extra number of neutrons, again absorbs a slow-moving neutron, and it immediately disintegrates. So it means the slow-moving neutron induces the nucleus, which was already unstable, to disintegrate. So the reaction is going to be called an induced nuclear fission reaction. It is induced. It is induced because it is started by the capture of a slow-moving neutron. It is induced because it is started by the capture of a slow-moving neutron. Yes, the uranium nucleus was unstable, but it wasn't disintegrating, not until a slow-moving neutron was absorbed. So in this reaction, each fission reaction described by the above equation results in 3 neutrons. So imagine if we have several uranium nuclei and each is giving us 3 neutrons. And remember, each of these neutrons can now move towards a certain uranium nucleus in the sample. So if these neutrons are absorbed by other uranium-235 nuclei, these two may become unstable, and therefore they would undergo what we call a nuclear fission, thereby releasing even more neutrons. So we started with one uranium nucleus, we started with one neutron in a sample, and it is absorbed by a single uranium nucleus. So energy is emitted plus 3 neutrons. It means now we have 3 neutrons available to trigger 3 other uranium nuclei in the sample, which will automatically result into 9 neutrons available to trigger 9 uranium nuclei in a sample, which means now the number of uranium nuclei triggered will go on increasing. So the reaction emits the reaction results into more and more amount of energy emitted as the reaction continues. This is what we are going to describe as an accelerated chain reaction. We started with a single neutron being absorbed by a single uranium nucleus, resulting into 3 neutrons which are now available to be absorbed by 3 uranium nuclei, which results into another 9 neutrons which are available to be absorbed by 9 uranium nuclei, and the process continues. So if the number of neutrons which take part in the chain reaction is controlled so that the number of fissions per unit time is constant rather than increasing, then the rate of release of energy can then be controlled. Of course, if the amount of energy goes on increasing, then we cannot put to use the process of nuclear fission. In order to be able to utilize the process of nuclear fission, we should be able to control the amount of energy which comes from the reaction. So if we can control the number of neutrons being emitted, then we can control the reaction. And therefore, a specific amount of energy needed for human use, can now be obtained from the reaction. And this is exactly what happens at a nuclear reactor or at a nuclear power station. So initially, this is what I was talking about. We started with the uranium-235-92. It absorbed a single neutron and it disintegrated to give us a barium plus krypton. But this was accompanied by 1, 2, 3 neutrons. And each of these neutrons was available for absorption. So let's just look at these 2 neutrons. So 1 neutron is absorbed by this one to give us again barium and krypton. Again, we have 3 neutrons. This one gives us barium and krypton, again plus 3 neutrons. So it means each of these neutrons in the sample can now go further and induce reactions of different uranium nuclei, resulting into what I called an accelerated chain reaction. And this is exactly what happens during an atomic bomb explosion. In an atomic bomb, you have several uranium nuclei, for example. And when you trigger one nucleus of uranium by allowing a neutron to attack it, it means this uranium nucleus which has been triggered is going to produce neutrons which will trigger the neighboring uranium nuclei, which will also produce neutrons which will trigger the remaining uranium nuclei, and the process continues. This takes a very short time, and therefore the atomic bomb becomes more dangerous as it continues exploding, because the amount of energy emitted goes on increasing if it is not controlled. That's why we call it an accelerated chain reaction. But we said if we can control the reaction by controlling the number of neutrons, then we can obtain a specific amount or the exact required amount of energy for our domestic use, for example. This is exactly what happens at the nuclear power station or the nuclear power plants. So what is used during nuclear power generation are what we call the control rods. These ones are made out of boron. These are made out of boron. We call them the boron rods. So we can control the uranium, we can control the number of neutrons emitted in this reaction. And if we can control the number of neutrons emitted in the reaction, then the reaction does not really accelerate. and therefore a specific amount of energy required for different purposes can be obtained, or the output energy can be maybe I will use the word constant. It can be made constant if we can control the number of neutrons which are being used in the reaction. And I'm saying in the reactor of a modern nuclear power station, some neutrons released in fission reactions are controlled. Two of the neutrons produced by the fission are absorbed by what we call boron rods. These are normally made out of boron. Boron has high affinity for neutrons. Therefore, boron tends to absorb the energy. It tends to absorb these neutrons, and the kinetic energy of the neutrons is converted into heat or thermal energy in the boron rods, so the boron rods can warm up. However, the neutrons, this neutron and this one here, incident on the boron rod is absorbed. That means only one neutron is allowed to further the reaction. So that means a constant amount of energy is therefore going to be emitted in this process, or a controlled amount of energy is going to be generated for domestic use, if I'm to put it like that. So this is what we are calling a controlled reaction, where we insert in a nuclear reactor where we have a boiler like this one, which has a sample of uranium. At the nuclear power station, inside this sample, they will insert boron rods, because boron rods have a high affinity for the neutrons. So depending on how much amount of energy we want, we can put in a specific number of boron rods. If we want a small amount of energy, then it means we shall insert many boron rods so that many neutrons are absorbed by the boron rods, so that the amount of energy coming out of the reactor is as low as possible. So I'm saying the kinetic energy of the neutrons is absorbed by the boron rods and is converted into thermal energy of the boron rods. So the boron rods will simply warm up. So this is what we call a controlled reaction. Definitions. So we have been talking about nuclear fusion and nuclear fission. So what is now the difference between these two? Let's start with the nuclear fusion. We said this occurs when two very light nuclei combine to form a more stable nucleus of greater mass, which has a higher binding energy per nucleon. Now, many times we shall confuse this. I would prefer to use a greater nucleon number. But what is important is that when the two very light nuclei combine, they will form a more stable nucleus, which has a higher binding energy per nucleon. Then on the other hand, nuclear fission is the splitting of a heavy nucleus into two lighter nuclei of approximately the same mass. They will be almost the same mass. And this is accompanied by the release of energy. But what is very important is that the resulting masses, the resulting nuclei have a higher binding energy per nucleon. So either way, if it is nuclear fusion, the binding energy per nucleon is higher. If it is nuclear fission, the binding energy per nucleon is also higher. So that is the difference between nuclear fusion and nuclear fission. Fusion, two light nuclei combine to form a more stable nucleus with a higher binding energy per nucleon. Fission, a heavy nucleus splits to form two lighter nuclei. There should be two lighter nuclei of approximately the same mass and a higher binding energy per nucleon. So either way, fusion or fission, energy is being released. Either way, fusion or fission, the resulting nuclei have a higher binding energy per nucleon. So that is the difference between the two. So to sum up all this, let's see where and when. What do I mean by that statement? Where and when? Where does it happen and when does it happen? So in both cases, these are at nuclear level. Whether it is fusion or it is fission, they are both at nuclear level. Whether it is fusion or fusion, they are both at nuclear level. But for fusion, two nuclei combine, that is fusion. And for fission, the nucleus breaks up, that is for fission. So fusion, combine. Fission, they split. But both of them, whether nuclear fusion or nuclear fission, they occur at nuclear level. That's why the topic or the chapter or the unit is called nuclear physics. Both of them are occurring at nuclear level. That's why the chapter is called nuclear physics. So whether it is fusion or fission, they both occur at nuclear level. Okay, so we now know the difference between nuclear fusion and nuclear fission. Let's distinguish the two terms using a graph. Remember we said for fusion, the lighter nuclei must combine. And as they combine, the nucleon number tends towards this region of stability. So for on the left-hand side, where we have lighter nuclei, the arrow must be pointing towards the peak. On the right-hand side, where we have heavier nuclei, the arrow must also be pointing towards the peak. So on the left, we have fusion, because the lighter nuclei must be combining. And as they combine, their nucleon number slightly increases, which means their binding energy per nucleon also increases. On the right-hand side, the heavier nuclei must split. In the process of splitting, they give us, or they would result into nucleons whose nucleon number is relatively less or tending towards the region of stability, around this region here where we have the peak. And in the process of doing so, the binding energy per nucleon of the resulting products is going to be higher. So fusion, lighter nuclei are combining, and the fission, heavier nuclei are splitting. So that is how we can distinguish the two using graphs. So both fusion and fission are processes that tend to increase the binding energy per nucleon of the particles involved, as shown by those arrows. A few things we need to note. Number one, although fusion reactions are the source of solar energy, that is the energy of the sun, it's true that fusion reactions are the source of solar energy, or the energy of the sun. We are at present unable to duplicate this reaction in a controlled manner on Earth. So fusion does not occur on Earth. We cannot harness energy from using a fusion process. The reason is very simple. This is because the nuclei involved in fusion have to be brought very, very close together. And to bring these nuclei together, yet they are both positively charged, we shall need conditions of extremely high temperature and pressure, only similar to those which are found at the core of the sun. Conditions of extremely high temperature and high pressure, only those similar to the ones found at the center or at the core of the sun. Why high temperature? Of course, as we shall see in a unit, or you might have seen a unit called ideal gases, temperature and thermodynamics. High temperature means high kinetic energy, because temperature is the average kinetic energy of the molecules. So high temperature would mean high kinetic energy. So it would mean at high temperature, the deuterium nuclei, for example, will have high kinetic energy to overcome the repulsive force between them so that they can fuse to cause the reaction. So reactions requiring conditions of high temperature and pressure are normally called thermonuclear reactions. Number three. Also note that neutrons are preferred as bombarding particles in nuclear fission, since we know that the nucleons carry no charge. Why can't we use electrons to induce nuclear fission? Why can't we use our protons to induce nuclear fission? Of course, the protons are going to be repelled. That means it would require again more energy to overcome the repulsion. The electrons will also be repelled, because if this is an atom and this is the nucleus, where we have the nucleus of the atom, around the nucleus, according to the nuclear model, we have electrons. So if you say you are going to bring an electron to bombard or to induce a nuclear fusion, remember there's an electron cloud surrounding the atom. So it will still also mean that the electron is also going to be repelled. So it is the neutrons which are used because they carry no charge, and because they carry no charge, we don't expect them to be repelled at all. So they can penetrate deeper into the nucleus without repulsion or attraction because they have no charge. So neutrons are preferred during nuclear fission because they carry no charge. They can penetrate deeper into the nucleus without repulsion or attraction. And why not electrons? I've also mentioned that the electrons will be repelled by the electron cloud around the nucleus, while the positively charged protons will be repelled by the positive charge of the nucleus. So the electrons are repelled by the electron cloud around the nucleus. The protons will also be repelled by the positively charged nucleus. So we prefer to use the neutrons because for them they will penetrate deeper without any repulsion. I think that makes some sense. So let's explore more examples before we leave this lesson. Oh, by the way, the energy given out during nuclear fission can be changed to electricity at power stations. I think this is what happens in many countries, Russia, I think, Japan, Korea, I think North Korea. The energy which comes from nuclear fission can be changed to electricity at power stations. However, this energy can also be used in the manufacture of atomic bombs because the process is the same. The process of an atomic bomb is the same. So if terrorists land onto wastes of nuclear products, they can use them to manufacture atomic bombs because the process is the same. So the energy can also be used in the manufacture of atomic bombs. Example number 1. One nuclear reaction that could occur when a nucleus absorbs a slow neutron is shown here. I think we have already seen such. Uranium-235 absorbs a neutron which is N10 to form uranium-236 to give us La, that is lithium, I think, and beryllium plus 3x plus y. The binding energy per nucleon. So they have given us binding energy per nucleon. Remember, to find binding energy per nucleon, we divided the binding energy by the nucleon number, which means to find binding energy alone, we would multiply the binding energy per nucleon by the nucleon number. For each of the products is given below. So they have given us the binding energies per nucleon here. Then identify X and Y and complete the equation. So I'll just try to complete it from here. So if I try to balance this equation, of course I know that this is going to be 1 and this will be 0. So proton number is 157 plus 35, it's already 92. And nucleon number is 146 plus 87. 3 times 1, that is 3 plus 87, that is 90. I think that is 236. So it means this one has no nucleon number, has no proton number. So this is most likely going to be gamma photon. So identify X and Y. So X is going to be a neutron, and Y is most likely going to be gamma photon because it has no nucleon number, has no proton number. So this is going to be gamma photon. That's what I think. They named this type of nuclear reaction because the nucleus uranium is splitting, so it is a fission reaction. It is fission. But because it starts by absorption of a neutron, you can be specific and you say it is induced nuclear. It's an induced nuclear fission. Then explain why neutrons are used to split uranium-235. We have said neutrons have no charge, so they can penetrate deep into the nucleus without any repulsion. Then estimate the amount of energy released. So to find the energy released, we must first find the binding energies. To find binding energies, we shall multiply the energies by the binding energy per nucleon. For example, this one, the binding energy here is going to be, the nucleon number is 235. I multiply nucleon number by the binding energy per nucleon. So I have 7.59 times the nucleon number, which is 235. So this is 17. This is supposed to be, I think this is supposed to be 6, not 5. Because we are considering the equation from this point here. So I'll say 7.59 times 236. So this is 1791.24. Then I have 8.41 times 146. The binding energy here is 1227.86. I have 8.59 times 87. This is 747.33. These are the binding energies after multiplying by the nucleon number. So estimate the energy of the amount of energy released. So I will just find the difference in the energy to see what has been released. So on the left hand side, I have LA, which is this, plus BR, which is this. So I'll sum up and subtract. So the amount of energy released is going to be 1, 2, 27.86 plus 747.33 minus 1791.24. I think this color is not good. So I'll add and subtract. So the amount of energy released is approximately 184 mega electron volts. Now you cannot sum up the binding energy per nucleon and you think it will be the energy released unless it is energy released per nucleon. We don't have anything like energy released per nucleon. So that's why I had to multiply back to remove the per nucleon part so that I just get back the binding energy, then I subtract. I summed up this because this is on the same side of the equation, then the other is on the one side alone. Then suggest how energy is released during this nuclear reaction. Remember I said energy is released in two forms. Energy is given as kinetic energy of the products. So there will be kinetic energy of La nucleus and Br nucleus. And energy is also emitted as gamma what? Gamma photon. So energy is emitted, is given out as kinetic energy of the products. That is, it appears as kinetic energy of La and Br, and energy can be emitted as gamma ray photon. It can also be heat. It can be emitted as kinetic energy and heat for La and Br, but most likely going to be kinetic energy of the products, such as the La, Br, the neutrons, and also energy is given as gamma photon because gamma photon is entirely electromagnetic radiation, which is actually energy. So kinetic energy of La, Br, the neutrons, kinetic energy of the products, that is the Br, La, and the neutrons, and then gamma ray photons. That is, those are the forms which energy takes. I think I solved this. So this slide just gives you a summary of the solutions that I've been talking about in more details. So X is a neutron and Y is a gamma photon. The equation is written correctly there. And the process is called the induced nuclear fission. I told you why it is called induced, because it starts by absorption of a slow-moving neutron. Then we explained why neutrons are used. We said neutrons are used because they are electrically neutral, they have no charge, and therefore they will be able to penetrate into the nucleus, into the uranium nucleus, without experiencing repulsion or attraction. And by the way, the neutrons are also readily available. It is easy to produce or generate neutrons in the laboratory. So I have done this, multiplying the binding energies with their nucleon numbers. Then I summed up and subtracted. And that is the binding energy, the amount of energy released. The third question was asking us to state the forms in which the energy takes. And we said energy is released as a gamma photon. Of course, it appears as kinetic energy of the products, that is La, Br, and the neutrons. So that is the form in which energy takes. Okay. Example number 12. When a fast moving neutron hits uranium 235-92, the nucleus breaks up into Mo, La, and 2 neutrons and 7 electrons. Calculate the energy released by 10 grams of uranium in this reaction. Okay, so 10 grams of uranium in that reaction. So first of all, we shall find the mass defect. The mass difference is going to be on the left hand side. So we have this on the left hand side. This uranium is giving us Mo plus La plus 2 neutrons plus 7 electrons. Okay, since they didn't ask for the equation, I will not write a full equation. So on the left hand side we have uranium. I don't know which side is bigger, but as long as we get the difference in mass. So I'll start from, oh, by the way, there is a neutron this side, because they said when a fast moving neutron hits uranium, so I have to add a neutron this side. So on the left hand side I have a neutron plus that, so the mass of a neutron is, where is the neutron? Okay, 1.009 plus uranium, which is 235.044. So that is on the left hand side minus. I'm just finding difference in mass. You can start from the right hand side. On the right hand side I have Mo, whose mass is 94.906 plus La, whose mass is 138.906 plus, we have 2 neutrons, so I have to say 2 times mass of a neutron, which is 1.009 plus, we have 7 electrons, so I have to say 7 times 0.005. So I have to press my calculator to get the mass difference. Okay, so from my calculator, the mass difference is 0.188 U. But because we want to calculate energy, I have to change this into kilograms. So this is going to be 0.188 times 1 U is 1.66 times 10 to the power of minus 27 in kilograms. So I have to check my calculator again. Okay, so the mass in kilograms is 3.1208 times 10 to the power of minus 28 kilograms. So calculate the energy released by 10 grams of uranium in this reaction. Let's first find the energy released in this reaction by one atom. So energy by one atom. The energy released by one atom, so we know that energy is equal to mc squared, or delta mc squared. When I substitute, this is going to be 3.1208 times 10 to the power of minus 28 kilograms. So this is giving me oh, by the way, this is I have, of course, I've multiplied this by 3 times 10 to the power of 8, and this was squared, which has given me 2.80872 times 10 to the power of minus 11 joules. So that is the energy released by one atom. Then let's find the number of atoms in 10 grams of uranium. So from ideal gases, the number of moles is given by the number of particles over Avogadro's number, which is the same as the mass divided by the molar mass. What is the implication here? So it implies that if I want to know the number of atoms in 10 grams of uranium, that is N is going to be the mass divided by the molar mass. Then I multiply this by Avogadro's number. So this is going to be, the mass is 10 grams. The molar mass of uranium is 235 grams. The nuclear number is the molar mass in grams. So this is 235 grams. We know that Avogadro's number is 6.02 times 10 to the power of 23. So how many atoms are these? So this is giving me a total number of atoms of 2.562 times 10 to the power of 23 atoms. So this is the number of atoms. But remember, the energy released by one atom was equal to this. So let's find total energy released. So the total energy that would be released by 10 grams is going to be the number of atoms times the energy released by one atom. So this would be 2.562 times 10 to the power of 23 times the energy, which is 2.80872 times 10 to the power of minus 11. So I'm just going to press my calculator. From my calculator, I have this as 7.195 times 10 to the power of 11 joules. So 10 grams will give us that amount of energy. You can check maybe I didn't press the calculator correctly, but at least I've tried. So we have the mass defect in unified atomic mass units. I changed it to kilograms. Using the energy equivalence equation, I got the energy in joules. Using the relations of number of moles to ratio of particles, ratio of mass, I got the number of atoms. Then I now found total energy by multiplying the number of atoms times energy released by one atom, which gives us that. Okay, so I think that is fine. Oh, what is this? Okay, so I think there are solutions here. Maybe I can delete. I can erase my solutions. Okay, so I think that is the solution, which is I think almost the same as the ones I've just given to you. Let's check example number 13. Given that uranium-238 equals to that and thorium equals to that in mega electron volts, 1U is 933 mega electron volts, helium is given as that, show that the nucleus of uranium can disintegrate by raising an alpha particle. Of course, if there is a difference in mass, then it can disintegrate by releasing an alpha particle. If there is no difference in mass, then the reaction is not possible. Then calculate the energy released in the process. So I'm going to use a different color so that let me use black. So uranium-235, I will start by writing the equation, I think, even though it's not necessary. So we have uranium, it is 238, proton number is 92, is disintegrating by emission of TH. Thorium, they have given us thorium, I think this is 144, not 234. Okay, it is giving us thorium 234, not 230, not 144, 234, and 234, 90, then plus an alpha particle, which is a helium nucleus, that is He42. I don't think there is a thorium 23490, but since that is how it looks like, let's give it a benefit of doubt. Show that the nucleus of uranium can disintegrate by releasing an alpha particle. So all we need is to find if there's a difference in mass. On the left hand side, we have uranium, whose mass is this. So we just need to check the total mass on the right hand side. So I'll simply say total mass on the right hand side is going to be equal to, we have TH, whose mass is 243.1165 plus helium, which is 4.0036. This gives us, I'll just press my calculator, Okay, so this is giving me 238.1203 U. So look at the mass on the left hand side, which is this one here, and look at the mass on the right hand side, which is this one here. If there's a difference in mass, then the reaction is possible because the difference in mass is compensated for by the release of energy. The difference in mass is compensated for by the release of energy. So I will simply say that since there is a loss or a difference in mass, the reaction is possible. The reaction is possible, and I'm saying the difference in mass is compensated for by the release of energy. So it means this side I would add energy because there's a difference in mass. Then calculate the energy released in the process. So of course energy, I'll just find them because they've told us 1U is 933 mega electron volts. I just find the mass difference and then I just find the energy equivalence. So the energy, the equivalence in mass, the mass difference is simply going to be left hand side. I have 238.12492 minus 238.1203. Okay, so this is giving me 0.00462 in unified atomic mass units. Remember, 1U is 933. So the energy released or the energy equivalence to this mass defect is going to be 0.00462 times 1U, which is 933. This is in mega electron volts. So I'll just press my calculator. So this is approximately 4.31 mega electron volts. So depending on how you round off your values, your answer may be slightly different, but very close to the same answer. Okay, so I think that is correct. Yeah, the solutions were given here, but I think there is just a problem here on this equation here. So this is going to be 234.90 for the equation to balance. Okay. So I've already solved this, even if I don't show the solution. The solution is correct, so I'll just skip that. Example 14. Given that the mass of PO is that, lead is that, helium is that, and 1U is 934 mega electron volts. State whether this is possible for PO to undergo an alpha decay. Calculate the mass defect of the reaction and find the total energy released. I think this is the same as the previous question. I will not waste a lot of time. If there's a difference in mass on both sides, then we just that difference in mass implies that energy is released, and the energy release is to compensate for the difference in mass. So if there's a difference in mass on both sides of the equation, then the reaction is possible. So we have PO is giving us Pb plus helium. So the total mass on the right hand side is the mass of Pb plus the mass of helium. And when I check from my calculator, it is less. So there's a difference in mass. So the loss in mass is compensated for by the emission of energy. So the reaction is possible. Then the mass defect, we just subtract total mass on the left hand side of the equation by total mass on the okay, so this is the equation, which I think it is correct. Then I got the total mass on the right hand side to be this one, which is different from total mass on the left hand side. So there's a difference in mass, which means the equation is possible because the difference in mass is compensated for by the energy released or by the release of energy. The mass defect, we just get the difference in mass on both sides of the equation, which is this, and then we just multiply with what 1U stands for to find the energy released in that reaction. So the energy released is going to be equal to that. Okay, so that is the energy released. Example 15. One kilogram of deuterium undergoes nuclear fusion only at very high temperatures of a few millions of degrees. This collision of deuterium nuclides is shown by the following reaction. So deuterium to give us helium-3 plus 1 neutron. Explain why nuclear fusion occurs only at high temperatures. I think I've already explained why it occurs only at high temperatures, because we said at high temperatures, the fast moving nuclei are going to have high kinetic energy. And because they have high kinetic energy, they can now overcome the repulsive force between them because they have the same charge. Therefore, they can now come close enough, and then the reaction is going to be possible. So high temperature means high kinetic energy. High temperature means high kinetic energy. So if they have high kinetic energy, they can overcome the force of repulsion between them so as to fuse. Low temperature would mean low kinetic energy, or low speed means low kinetic energy. And therefore, they can easily be repelled, so the fusion reaction does not occur. So that one is very, very easy. Then suggest a method to attain such high temperatures on Earth. Remember, we said nuclear fusion is at the present not easy to model on the Earth's surface, but vast amounts of heat or high temperatures can be generated during atomic bomb explosions. So high temperatures of millions of degrees from the fission reaction, that is fission, that is during atomic bomb explosions, such fission reactions can generate high temperatures. So such high temperatures can now be used to induce or to activate fusion processes. So we can use the fission to induce fusion or to activate fusion, because the fission can generate high amounts of energy, that is during an atomic bomb explosion. Then calculate the amount of energy released by 1 kilogram of deuterium. 1 kilogram of deuterium. Okay, so this would require a lot of space. So let me try to see if I have space in the next slide. So I'll need to quote some of these. 1 kilogram of deuterium. A factory uses 10,000 kilowatts of electrical energy per month. Calculate the approximate number of fusion reactions that is required to keep the factory running for 1 year. So the time is 1 year. This is power, kilowatt hour. I think kilowatt hour is energy because it's power times time. So they have given us the rest mass of deuterium, the rest mass of helium, the rest mass of a neutron. Okay. So the first part of the equation, I think I've already answered this, where I said in part A, at high temperatures, the fast-moving deuterium nuclides will be able to overcome the strong electrostatic repulsion between them and approach each other. Reason: High temperature means high kinetic energy. Therefore, they can easily overcome the force of repulsion. I've already explained that. But at low temperature, the deuterium nuclides have low speed. That means they have low kinetic energy. They can easily be repelled. So they are repelled away from each other, and therefore they cannot come close enough to fuse. The reaction will not occur. Then I also answer the question which was talking about why, how we can attain such conditions of high temperature. And I said atomic bomb explosions can generate vast amounts of energy, so they can generate high temperatures, millions of degrees. And such high temperatures can be used to activate fusion processes. So that's the only way we can generate high temperatures found at the core of the sun is again by relying on nuclear fission, for example, during atomic bomb explosions. Then for part two was asking us to find, sorry, part C was asking us to find, it was asking us to find, to capture the amount of energy released by 1 kilogram of deuterium. So I've already solved this here. From this equation here, total rest mass of the 2 deuterium nuclei, that is the total mass on the left-hand side, we sum up the masses. We have 2 deuterium nuclei, that's why I multiplied 2 times the mass of each deuterium. Then on the left-hand side, on the right-hand side, we have helium, this whose mass is that, and a neutron whose mass is that. So this is total mass on the left, on the right-hand side. So we need to find the mass defect by subtracting the two masses. And then to find the energy released in such a reaction, we have to multiply the mass defect, which should be converted into kilograms, times the c squared. And when I pressed my calculator, this is what I obtained. Then energy released per deuterium. Remember, there are 2 deuterium nuclei, so it means each deuterium nuclei will release an amount of energy, which is this total energy released in the reaction divided by 2, because there are 2 deuterium nuclei. So each deuterium nuclei releases that amount of energy. Then the question wanted us to find the amount of energy released by 1 kilogram of deuterium nuclides. So we needed to find out how many deuterium nuclides or how many deuterium nuclei are in 1 kilogram. So still using number of moles equals to number of particles or number of nuclei divided by Avogadro's number, which is the same as mass over the molar mass. I made n the subject, so n is equal to mass over molar mass times Avogadro's number. The mass is 1 kilogram. The molar mass of deuterium, because it is H21, this is molar mass in grams, 2 grams. So I had to change it to kilograms, so I divided by 1,000. So kilograms, of course, cancels. When I divided, I got the number of deuterium nuclei in 1 kilogram to be that. So the energy released, to obtain the energy released in 1 kilogram, I got the energy which is released if we have 1 deuterium nucleus times the number of deuterium nuclei, which gave me that amount of energy. Then the other question, I think it was asking us to calculate to capture the approximate number of fusion reactions that is required to keep a factory running for 1 year. Yet it uses 10,000 kilowatt hour. The energy was 10,000 kilowatt hour in 1 month. So since I already know the energy released by 1 deuterium nucleus, and I mean the energy released in 1 reaction is this one here. The question wants us to find how many reactions. How many reactions? So I just need to change the energy from kilowatt hour to joules. So this is what I did. I just converted the energy from kilowatt hour to joules. Remember, they gave us energy in kilowatt hour per month. It was per month, so this was it was it 10,000? It was 10,000 kilowatts. So this is 10,000 kilowatts. So the kilo is times 10 to the power of 3. Then This was per month, but there are 12 months in a year, so the time is 1 year. So this is 12 times 3,600. There are 12 months in a year. Then this is 1 hour. Because it was kilowatt hour, this is 1 hour. 1 hour is 3,600. Then this is time. There are 12 months. So this is the time is 12 months, which is 1 year. So when I multiply, the energy per year is going to be that. I don't know whether that is correct because I made a mistake there. I have to check it again. So I have 10,000 exponent 3 times 3,600 times 12. Yeah, I think this is correct. It is just a typing error. So there's a 0 which is missing there. 10,000 times 10 to the power of 3. This is watts. Then hour, which is because it was watt hour. Then times 12 because this was from 10,000 kilowatt hour per month. But then there are 12 months in 1 year. So that is the total amount of energy required. But remember, each reaction gave us this amount of energy. So I had to divide to find the number of reactions. Number of reactions required is going to be that. It is not in joules, it is number of reactions, so there is no unit. Okay, so I think that is correct. You can also check and verify. If it's wrong, you can always leave a comment. I don't mind. Let's check example 16. Given that calcium 4020 has that mass, hydrogen has that mass, barium has that mass, and 1U is 932 mega electron volts. Write down the equation for the formation of calcium nucleus and hence calculate the binding energy for calcium. Then part B, in the fusion reaction of this is deuterium and tritium to give us helium-4, how much energy in joules is released? They've given us the masses here. So for part A, I think part A is very easy. Write down the equation for the formation of calcium nucleus. So it is calcium which is being formed. So it means the rest are going to be on the left-hand side. So I'll say, let me see, I'll say 20H11 plus barium. Barium is 10 to give us calcium, Ca 4020. So the only thing which remains is to balance this equation. So the proton number should be 20. And of course, barium, I don't know whether this is barium, but this is most likely going to be, okay, whatever it is. So this is, because this is 0, it means the 20 will be here. So that the proton number is 20. So now the nuclear number is also 20. So if I put here 20 again, the nuclear number now becomes 40. So it is balancing. But I don't think this equation chemically exists anyway. Write down the equation and hence calculate the binding energy for calcium. So we just find total mass on the left-hand side and total mass on the right-hand side. Of course, by the way, this will be accompanied by the release of energy. So if there's a difference in mass, then the reaction is possible. So we find total mass on the left-hand side, which will be this plus this. Of course, we have to multiply this by 20 because we have 20H11 and 20Ba10. So I have to multiply this by 20. I also multiply this by 20 and I sum up. Then I subtract this one here and see if there's a difference in mass. So that will be the mass defect. Then from energy is equal to mc squared, I can find the binding energy. Or Since they told us that 1U is equal to 932 mega electron volts, I don't need to use E equals to mc squared. So I'll just multiply the mass, the difference in mass or the mass defect by 932. Then for the second part, of course, I'll find the mass defect by finding total mass on the left-hand side minus total mass on the right-hand side, or total mass on the right-hand side minus total mass on the left-hand side. Irrespective of whether I get a negative, I am interested in the difference in mass. So when I find the difference in mass, I just use E equals to mc squared, and I find the energy. I think I solved this. Yeah. So this is what I was talking about for the equation. I've already talked about this equation. Then the mass defect, I summed up total mass on the left-hand side minus the mass of calcium that is on the right-hand side. So the binding energy, I just multiply the mass times what 1U stands for. For part B, I got the mass defect by getting the difference in the mass on one side, which is deuterium plus tritium. Then I got the mass on the other side, which is a helium plus a neutron. So the difference in mass was that. Then using E equals to mc squared, I just multiplied by 3 exponent 8 squared, and this is what I got as the energy. You can also press your calculator and verify. I might have made a simple mistake. Okay, so having gone through all those examples, I think you should also be able to try out the following self-check question. A nucleus, a stationary radium nucleus may decay spontaneously into a radon nucleus and an alpha particle as shown in the figure below. As shown below. So this is the equation. The rest mass of these nuclei are shown here. What physical quantities are conserved in this nuclear reaction? By the way, in every nuclear reaction, 4 quantities are conserved. Number 1 is proton number, which is the charge. Number 2 is the nucleon number. Number 3, momentum is always conserved in every reaction. And number 3, we have always been saying that whenever there's a difference in mass, energy is emitted to compensate for the difference in mass. So we say mass energy is conserved. So the quantities, I think I gave the quantities which are conserved: proton number, nucleon number, momentum, and mass energy. Those are quantities which are conserved. Proton number, nucleon number, and mass energy, these are conserved. Then the answers I expect you to obtain when you calculate this, I expect you to obtain 4.95 mega electron volts for part B. I expect you to get 7.3 times 10 to the power of minus 12 meters for part C. In case you find any challenge, you can always leave a comment. Okay, and then lastly, you can also try out this one. A high-speed alpha particle collides with a stationary nitrogen nucleus, which is given by that. Identify the unknown nucleus X and state the number and type of particles which form this nucleus. You can try to balance, because this is a gamma photon. So we have proton number is 7 plus 2, which is 9. On the right-hand side, we only have 1, so this is going to be 8. Z is going to be 8. Then nucleon number, we have 18. And on the right-hand side, we have only 1, so this is going to be 17. So that is 17. Identified unknown nucleus X. So that is X is 17, 8, which is most likely, I think that is that an isotope of oxygen, I think? And type of particles which form this nucleus. Then, of course, that is going to be chemistry. Calculate the minimum kinetic energy of the alpha particle. So that one you can calculate minimum kinetic energy of the alpha particle. They have given you the constants down here. You just find the difference in mass on both sides. Then calculate the minimum velocity of the alpha particle. If I have the energy, then of course the energy is going to be emitted as kinetic energy of the alpha particle. If the energy of the gamma ray photon is negligible. So if I have the energy of the alpha particle, I also know that kinetic energy is equal to a half mv squared. So I'll just equate to a half mv squared. Since I know the mass of the alpha particle, then I'll find the speed. Describe the transformation of the kinetic energy of the alpha particle after the reaction. The transformation of the kinetic energy of the alpha particle. In other words, what is the fate of the kinetic energy of the alpha particle? What does it become? So you should be able to think about such answers or such a question and come up with an answer. I think I'm very tired and I should stop here.
What did happen to the last 10?